Hello, welcome everybody to the second talk in this AI for Automation lecture series. It's my pleasure to introduce our distinguished speaker, Dr. Subbarao Kampampati today. I have known him for many years and followed his work in the area of AI. A bit of introduction about Dr. Subbarao Kampampati. He's a professor of computer science at Arizona State University. He studies fundamental problems in planning and decision making, motivated in particular by the challenges of human-aware AI systems. He is a fellow of the prestigious organization AAAI, that is the Association for the Advancement of Artificial Intelligence, American Association for the Advancement of Science, and Association for Computing Machinery, and was the NSF Young Investigator. He was the president of AAAI, a trustee of International Joint Conference on Artificial Intelligence, and a founding member of Partnership on AI. Dr. Rao's research, as well as his views on the progress and societal impacts of AI, have been featured in multiple national and international media outlets. He writes a column on the societal and policy implications of the advances in AI for The Hill. He can be followed on Twitter, and you can see all his Twitter links and LinkedIn links. And I follow him on Twitter, and often I'm amused by the insights as well as the humor with which he shares those insights. Rao, it's a pleasure to have you here. The floor is yours.
Thank you. So you guys can hear me, I assume. Thank you, Rama, for that kind introduction, and thank you all for tuning in. So I am planning to talk to you about some work that we have been doing for several years in my group on getting AI agents to interact and collaborate with us on our terms, which is basically getting AI to work with us rather than against us. So the surprising thing about this topic is that it should not be something that is somewhat surprising in any way, but because if you look at like the popular culture, if you see any movie on AI, computers are definitely working with humans. I mean, starting from HAL in 2001, which, you know, with its very sort of sinister voice, to Her, to Ex Machina, as well as the books like Ian McEwan's Machines Like Me and Kazuo Ishigura's Clara and the Sun. Computers, the AI systems are supposedly working with humans, right? That's what everybody outside AI seems to think. But you know that within AI, there's been a bit of a curious ambivalence to humans for quite a long time. Our systems seem happiest either far away from the humans, you know, and happily on Mars somewhere, or in adversarial stance, you know, trying to beat humans in various narrow domains such as chess or Go or every possible game that you can think of. So it's almost strangely, it's as if AI systems and AI researchers want to help humanity. It's some of the people we don't seem to be able to stand, paraphrasing John Lennon. And so I've been thinking about this for quite a while, you know, for at least the last decade or so. And back 3 years back, when it was my turn to give like the presidential lecture at AAAI, I talked about these challenges of human-aware AI systems. You know, how do you develop AI systems that can collaborate with us, that can provide support to us, rather than being just purely and fully autonomous by and of themselves, which is basically what sort of AI research has focused on originally. And in fact, we basically looked at I looked at these issues of why isn't human-aware AI systems all over the place already? Why should we be pursuing it? And, you know, some of the challenges in making that happen. And then that actually, some of those challenges came up as the AI magazine cover article last year. You can take a look at it. And as Rama pointed out, I also write a bunch of public interest columns. And so there's like a recent one on will AI systems get along with us only if we design them that way. So it's like the idea of getting AI systems to work with us is something that has to be deliberate because we need to design, we have to develop systems that have the ability to collaborate with us. So that's a direction that we've been pursuing. So human-aware AI systems are needed basically, in all sorts of scenarios. Like you, of course, have situations such as intelligent tutoring systems and social robotics, for example, kids playing with robots and so on, where the AI systems have to actually interact with the humans. But even those are not the only ones, really. You want your AI systems to work with you, with the human in the loop in a variety of scenarios, whether in terms of assistance, human-aware digital personal assistants, or an office and hospital assistants, or in teaming, elbow-to-elbow teaming on factory floor, or remote and cognitive teaming, and also, of course, providing, factory robots that sort of not only work with you, but also provide explanations as to why they're making the decisions they're making. This has sort of become, over the last couple of years, this has become a big national priority right now. In fact, US national AI priorities mentions human AI interaction as the #2 priority. And then, of course, there is a whole bunch of ARPA programs, DARPA programs, including Assist, Adapt, and PGT, which are all essentially looking at how to get AI systems to be assisting humans as against just being autonomous without caring about humans in the loop. And to some extent, there's this area called HCI that many of you are familiar with, human-computer interaction. And to the extent AI is everything nowadays, HCI will become really human-AI interaction. And it sort of changes the kinds of issues that we have to handle, expands the scope of HCI too, not only expands the scope of AI, but also expands the scope of HCI. So what we do in my group has been a particular slice of this. We have focused on explainable human AI interaction. Our setting involves essentially collaborative problem solving, where AI agents provide decision support to the human users in the context of typically explicit knowledge, sequential decision-making tasks. The two parts, sequential decision-making task basically means it involves a sequence of actions to be done, so sort of planning tasks. And these are also explicit knowledge tasks. There is this distinction I would like you to keep in mind about tacit versus explicit knowledge. Explicit knowledge ones where you actually can verbalize the knowledge that you're using. And so the interactions are also kind of verbalizable. Of course, some of the interactions between human interactions are actually tacit interactions. I just sort of gesture to you as again speaking to you, and you sort of read into my gestures. That is also part of the human AI interaction, and that has been typically looked at quite a bit in the human-robot interaction community. But we actually look a lot more at the explicit knowledge scenarios. And we assume that the AI agent has sort of either a prior access to the human's model of the task, or actually is able to learn it. In fact, these models become important, as I'll see in a minute, because a lot of how to help the humans in the loop is dependent on the AI system's view of the human's model of the task. And so we've been developing frameworks for proactive explanations based on certain technologies, one of which I talk about is model reconciliation, and also on-demand file-based explanation. So the humans in the loop can ask the AI system, why did you do this decision as against this other decision? And the system will be able to provide an explanation. And the kind of explanation it has to provide should not be soliloquy. In fact, when we explain our decisions to people, we don't talk to ourselves, we're talking to them. So the explanation has to make sense with respect to the model of the task the listener has, not the model of the task you have. And that winds up being very important to provide sort of an explainable interaction. And of course, we develop these, and also kind of one of the tricky slippery slopes of human in the loop AI research is we all are humans. We tend to think that we know what humans want, and so we'll just write a technique and then assume that should help humans. That has been shown to be pretty, yes, whatever, dumb idea in many cases. And so you actually have to carefully evaluate the effectiveness of the technologies that you're developing. And we do that with the sort of IRB approved systematic human subject studies. So the example applications, and so since Rama pointed out to me that I should try to say as much about the applications as possible, because many of the people dialing in are a lot more interested from that perspective. So I just decided to say a few things upfront about the kinds of applications we look at before getting into the theory and how we do it. So the example applications that we look at are at least of two types. One is the embodied interaction. So for example, on the left-hand side, you have a robot which is on the scene. In this particular case, imagine this as a mock search and rescue scenario. So it's a robot is on the scene of the actual building, which might need search and rescue. And then the human commander is out somewhere remotely interacting with the robot. And so in the beginning, essentially, they might start with the same model of the environment, but as the robot actually walks around the environment, it might get more information. Things like certain areas have collapsed or certain areas have opened up. And so this sort of makes the model of the task that the human has different from the model of the task that the robot has. And so this sort of winds up getting these misaligned expectations. The humans are confused as to why the robot is doing what it's doing, and the robot either has to conform to the human's expectations or to provide explanation. That's one class of explanation. Applications that we'll look at. I'll give you some examples as we go forward. The other is decision support systems. There is no embodied robot anymore. So in the first one, actually, the robot is doing the actions and the human sort of is somewhat of the more observing scenario in that particular set of applications. In this second one, the human is in charge. Human is at the steering wheel. They are trying to make mission plans, sequential decisions for some certain tasks at hand. And what the AI system is doing is sort of looking over the shoulder and trying to give them additional suggestions. And when they provide a suggestion, one of the important things for decision support systems is that the suggestion has to be sort of understandable in the context of what the human is trying to do in terms of the plan that they are developing. So that's the second type of application. So you'll notice that they look different. One has robots, one is just a bunch of it's basically a software artifact on which the humans are doing the planning, the generating the plans. But it turns out, and I hope to get this across to you, that most of the technical issues, they are quite similar in both these problems. One of the other interesting things is that while this is a set of applications that I've been looking at, I have this distinct advantage that I have moles in IBM. It turns out that two of the former students are actually at IBM Research, the Karthik Talamadupula and Tadhagata, and they have actually been doing a bunch of applications at IBM using the technologies that are connected to the ones developed in my lab. So even though I won't go too much into detail about these, but I just want to tell you that there is actually what being done on the IBM research side and has been done, which uses the same sorts of technologies that we have developed here. So in particular, there is this Mr. Jones, which is this sort of smart room, which tries to help people while they are making decisions. So this is sort of like a much more fancier decision support system. That was that one kind of application. The other, the very recent one actually is this D3WA plus, which is a system where the humans are developing dialogue models, dialogue plan models. And if those models are wrongly specified by the humans, sometimes there may be wrong behavior shown during the dialogue, AI bot dialogue, and the humans would then have to debug these models that they wrote themselves. And it turns out that helping them debug winds up being again a smart decision support, and you will have to sort of provide explanations as to why, for example, a certain impossible plan, a certain plan could not be developed before, and that sort of explanations can then be used to guide, to help the human to make changes to the model, which will then be propagated. So this is sort of a symbolic debugging plus plus sort of a thing that uses human in the loop, explainable interaction technology. So this is like, a force general class of application. These two, the second two are from at IBM, and the other two are the ones that we typically do in my lab. So that sort of gives you an idea. As I go into more abstract notions of models and machines working with humans and trying to make model reconciliation, it's all being done in the context of these kinds of problems. So that will give you an idea. Okay. So now let's see, what does it take for AI agent to show an interpretable behavior in the presence of human agents? And our main point, and it's not a particularly new point from a cognitive psychology perspective, but it's sort of newer in AI side, is that for you to be able, for an AI agent to interact fluently with humans, it needs to be able to manage mental models. And for those of you who may not have heard of Sally-Ann test, let me just point out the Sally-Ann test there on the right-hand side. This is basically shown to tell that kids, very early on realize that their model of the world is different from the model of the world that other people have. For example, in this particular case, Sally in red shirt comes in and puts the ball in the yellow box and goes away. Then Anne comes in the blue shirt and then takes the ball from the yellow box, puts in the gray box and goes away. And you seeing all this, you are an observer. You could be a kid in this particular case. And when they do these experiments with the kids, then they ask, essentially, now Sally comes into the room and Sally will be looking for her ball, and they're asking you, the observer, where would Sally look? And the earlier in the life, the kids below 3 years age, etc., tend to think that Sally will look in the gray box, because after all, the observer knows that the ball is in the gray box, so Sally will also know it, and so Sally will look for it. And of course, after 4 or so, the kids basically laugh at them and say, of course, Sally won't look at gray box, Sally will be looking at yellow box. And in fact, surprisingly enough, this realization that what you believe and what other people believe are different is the basis of lying, right? So I kid around that when my son, started telling his first lies, he tells a lot more now, but when he was young, when he started telling his first lies, I was ecstatic because I knew that he has a working brain and he is able to realize that his model of the world is different from the model of the world that other people have and the beliefs. So this has to be modeled in the systems that interact with humans too. And so the sort of the overview that I'm going to use for this talk is that effective human AI interaction requires AI systems to be able to manage human mental models. And these mental models are not just the human's model of the task, but also the human's model of the robot, because that is also important in terms of expecting the kind of behavior that the robot or the AI system will be showing you. And managing mental models brings up both inference and learning challenges, in particular, the ability to show behavior that is conforming with the expectations humans have, and when it cannot be conforming, providing an explanation, but the explanation has to be in terms of the differences between the AI agents and the human's model of the world. And then, of course, we also evaluate these frameworks. And if I have time, which unlikely, I also go into the point that mental modeling, as I mentioned, also opens up all sorts of interesting worries about what AI agents can do to humans in the loop. We keep worrying about deep fakes, but really the things that you need to worry about are head fakes. With your AI agent essentially making you believe in untrue things. Variations of that are already happened in social media. In particular, I would say that most people using Facebook kind of applications don't quite realize that they essentially are modeling them. And the fact that they don't realize it can be seen to be one of the biggest reasons why the kind of misinformation as well as user manipulation happens quite rampantly on these kinds of platforms. Now, of course, that is the downside. Every technology has dual uses, the positive uses as well as negative uses. And if you want AI systems to work with humans, they do have to be able to model the humans in the loop. Those are the positive uses. But then when you do that, you are also able to open the Pandora's box of the ability to manipulate them. And those are the other ones that we have to control. So that's the sort of things that I want to get across to some extent. And I should mention that obviously I mostly am the talking head here. Much of the work I am talking about is done by students and my collaborators, all the students there. And in fact, on top is Tathagata, who is actually at IBM research at Cambridge. He got done, like, I think, a couple of years back, and he's recently got his IEEE AI 10 to Watch award. So he's one of you guys. So, in case you have more questions about what I'm doing, you can talk to him or talk to Karthik too. Okay, so let's start with the tale of three models. I keep talking about mental models and managing the AI systems having to manage the mental models of the humans in the loop. So what are these models, and what sort of representations are we using for these models? Essentially, I can think of models in terms of the initial state, the goals, the actions, and observations, as well as the plans that each of the agents have. For the kind of work that we do, often we tend to use these relational descriptions of the models for actions, essentially relational actions with preconditions and effects. When the preconditions are holding, then the effects will be holding in the world. And so these are what's been called the planning domain description language in the automated planning community. That's the default models we use. However, much of the development we do in our work is actually agnostic to the specific representation of the models. You can also be using the SEES techniques if you are into, like, Markov decision processes with atomic representations, for example. That also can be done. And in fact, we have done some of that too. But I'll assume, for the purpose of this talk, that the models are given in terms of these action, precondition, effect representations, and the initial states and the goal states are in terms of relational state variables. So, if you have just the one single agent in the world, you have a model of the world. This is MR. I'll think in terms of a robot, which has the model MR of the world. And then basically it can use that model and its goals and its initial state to come up with, like, a sequence of actions that will achieve those goals. This has been called the usual planning problem. And basically there's a ton of work that you can do within that. That's a single agent planning. That is, you don't take about other people, certainly not humans in the loop. And, you're trying to generate the decisions, the plans with respect to that. Now, as soon as you put the human in the loop, then the tricky problem is that, first of all, humans might have a different model of the task than the robot. And the robot then essentially needs to have some approximation of the human's model of the task so that it knows what possible misalignments might occur with respect to what it is doing and what the human is doing. And in fact, this first level of mental model, that is, the robot now has an approximation of the human's model of the task. This is what you wind up using oftentimes in most assistive technologies, when, for example, these assistants recognize the intent of the human in the loop and are also able to project their intentions and their goals to the human. There's a lot of work in this particular area, but this is some of the work that we have done, including, for example, in this case, the intention recognition is being actually done in a tacit way. You're actually not doing in an explicit knowledge scenario. So this guy, Sachin, in the video is wearing like a primitive BCI, brain control computer interface, with which the robot is able to actually realize which blocks that Sachin is trying to reserve for himself so that it's avoiding touching those and using the other blocks to make it stack in this particular case. So that is intention recognition. That is sort of the robot trying to figure out the human's goals, humans intentions, and also humans model of the world. And then similarly, in the work that we have done, we also have looked at the intention projection, where the robot essentially tries to project the things that it is trying to do into the human. Again, this can be done explicit knowledge wise, but in this particular set of experiments, we were actually doing it sort of by projecting them into this augmented reality lenses, the HoloLenses. So this is essentially the robot using MHR to sort of make sure that the human is, that it's keeping track of what human is trying to do. Okay, that is sort of not the main point of my talk. The real main point of my talk today is the second order model. So humans, as soon as humans look at anything as sort of a tool or a partner, basically they start making a model of that particular tool, right? Or the partner. In this particular case, the humans will also have an approximation of the robot's model of the environment. So what is the robot's task model? And so humans will be using that in the back of their head in interpreting the robot's behavior. The whole point of interpretability is interpretability to the humans, not to the robot. So when the humans are talking about is the robot behavior interpretable to me, they are thinking in terms of their model of the robot and whether the robot conforms to their model or not. So that is MRH, not MHR, but MRH. And then the robot now has the second thing that it needs to approximate. It needs to also approximate MRH. It not only needs to know what the human is thinking, but it needs to know what the human is thinking of the robot. And that second part is what is useful for the robot or the AI system to ensure that its behavior is explicable, that is understandable to the human in the loop. And when it is not, provide an explanation as to why there is a difference. Okay. So I also want to mention that the approximations MRH and MHR, these are expectations on the models. They don't have to be executable in the world. These are sort of giving the robot an approximate idea about what the human is trying to do, as well as what the human thinks it is trying to do. And so these models don't necessarily have to be represented in the same way the original models are. I'll show you a little later that we oftentimes actually find implicit representations for these models in terms of labeling decisions, labeling procedures, and so on. And so that's sort of important because these sort of give soft constraints for the robot in terms of what to expect and what to expect humans' reaction would be to its behavior. So given this, sort of in terms of these models, the interaction cycle between the humans and the AI system would be, start with an initial for the robot to start with an initial estimate of what the human thinks the robot's model is, MRH, and then the AI system is in a loop. Either it is following the model that the human has of itself, in which case it is conforming to it. So MRH, conform to MRH. There are notions of explicability, which we'll talk about right now, and also predictability, which are sort of parts of interpretable behavior. So do humans understand what the behavior that the robot is showing, and are they able to predict what the next step would be? These follow from the robot actually following humans' model of it. Okay, and the model communication part is basically, rather than conform to what the humans think of the robot essentially tells the humans, here are the changes you have to make to your beliefs about my model so that you will start understanding why I am doing what I am doing. This ultimately, when you cannot do what people expect you to do, you need to explain why you are deviating from their expectations. And those explanations are always in terms of changing their beliefs about your abilities and your goals. And so that's what model communication is. And there are interpretable AI notions such as legibility, explanation, as well as even changing the environment that can come into play in making sure that the model communication occurs. I will speak today more about the explanation part, how the agent can communicate changes to MRH through explicit communication modes, and how do you make sure that you computed the least number of deltas, the model differences to communicate. So that's sort of model following and model communication. Let me sort of walk you through these two pieces in the context of like that robot example that I had. So the robot's task model may be different from the human's expectation of it. And as a consequence of it, plans that are optimal to the robot may not be optimal with respect to the human's expectation. These become inexplicable plans, so the humans are unable to see why the robot is doing it this way as against a different way they expected. At that point, the robot has two options: conform to the expectations or change them. The conforming to the expectations is model conformance, and changing them is model communication. And the first one is explicable planning, the other is plan explanations. I want to kind of show you this, illustrate this to you in the context of the picture that one of the applications that I mentioned earlier, this mock search and rescue scenario. So as I said, the human is an external agent. They're outside of the environment, but communicating with the robot. And the robot, actually, they both start with the same model of the environment, but then the model that the robot has evolves because it sees the ground reality, and certain paths are closed and paths open up, etc. So with respect to that, given where the robot is supposed to go from where it is, the humans might be expecting that it will take the shortest path, which is through this particular corridor, and it turns out that that corridor, in this case, it's closed. We assume that it was closed by rubble. We put a little thing there, and so that at this point, to conform to what the humans expect, the robot essentially has to basically clear the path and then go through it. That's the only way it will be explicable, because the humans are expecting it to come through that particular path, and so it will somehow go through it. Okay, that's the explicability. And notice that explicability in this particular case, once this path is closed, the robot being forced to go through it has increased the cost for it of traveling to its goal, because in fact, after all, there is this extra, stuff that it has to do in terms of clearing up the path. And so in general, when an AI system has to conform to the expectations of a human in the loop, its execution cost increases. And so to make sure that the plan that it's developing is actually explicable to the human in the loop, it not only needs to look for the plan that's optimal to it, but also make sure that the plan it is doing is close enough to the plan that the humans are expecting. So you are essentially doing this a multi-objective optimization. In this case, I sort of combine them into a single objective, where the cost of the robot plan plus alpha times the distance between what the robot is trying to do versus what the humans would expect it to do in that scenario. And the robot essentially has to simulate this using its approximation of MRH and use that to make sure that its behavior is as close to the human's expectation as possible. That's the explicable plan. The problem with conforming to expectations, as I mentioned, is it can be quite costly, because essentially, I think you all know, we as humans know that the advantage of conforming to people's expectations of us that we never have to speak up, because you do exactly what people are expecting. They never expect any explanation from you. But on the other hand, your life can be pretty miserable. In this case, the robot's life can be miserable in terms of its cost of execution increasing. So the second idea is essentially to communicate the changes in the model. So the reason the human is expecting the robot to go through that short path is because that is the shortest path in the model that they both shared in the beginning. But now the robot's model of the environment has changed. And so in fact, the shortest path is no longer this. It's a different path, which was the second shortest path previously, let's say. And so the robot needs to sort of tell the human what they need to change about the beliefs about the environment so that they won't have this wrong expectation. And in this particular case, they essentially need to tell that the corridor, a particular corridor is closed, and it needs to tell them while it is basically picking the next level. And so So what I showed here is, in this particular case, the robot didn't bother trying to remove the obstacle from the previous path. It just is yelling at the top of its head saying that that particular path is closed, and it's then taking a different path. So the explanation part is telling which piece changed. Now notice that the robot could always have said, at any given point of time, just say everything that it has seen about the change in the model. It could have just communicated to the human, and that would be an explanation. That would be a non-parsimonious explanation, because if you say everything to the human in the loop, that will increase their cognitive load. So the important thing here in providing explanations is to come up with the minimal changes that the human has to make to their MRH, such that the robot's behavior winds up being the optimal behavior in this changed model for the humans too. And that's what is computing explanations. And we can actually formally state this as a search in the space of these models, these sort of PDL sorts of models, where this search is being done by the robot, in essence, in trying to make sure what would be the minimum changes that it needs to communicate to the human about their mental model, about the robot's environmental model. And then once those are done, its hope is then that the humans will realize that the path that's taking is indeed the optimal path in this changed model. It turns out that although I talked about explicability and explanation as if they are two very different pieces, they can actually be combined into the same single unified framework. Just before everything shut down last year at III 2020, we presented this expectation-aware planning framework, which essentially involves the agent doing both communicative actions or explanatory actions and ontic actions. Actions which have effects on the environment versus actions that have effects only on the mental models of the humans, typically the communicative actions. And then you can combine both of them. And then there's this whole area called epistemic planning that has been looked at back in the day. Now, in fact, there are ways in which this expectation-aware planning or epistemic planning can be compiled down to essentially a single agent deterministic planning scenarios. And so it's sort of more efficient than the worst case scenario, which is epistemic planning in general has very high complexity. But this particular subclass, you can do it reasonably efficiently. And when you do this, in essence, the robot is in essence saying, how much will I change the human's model and how much will I conform to them? So it's sort of meet halfway. You tell them, change these aspects of your belief about my model, and then I will conform to the rest of your beliefs about my model. And so that's both of combining explicability and explanation. And then there's a way of compiling this into single agent planning that I would not even go into right now here. So if with this sort of technology, coming back to the applications, you can essentially, in addition to the cute robot demos that I've shown, which are sort of embodied robot-human interaction, you can also be thinking in terms of software systems with the humans, for example, making plans and decisions in command and control scenarios, in scheduling scenarios, and also, of course, in things like intelligent tutoring systems. We applied these sorts of this sort of explainable interaction in all of those. And so, for example, this is a case where, with respect to mission planning, with a human making plans and the AI system providing suggestions as to how to expand the plans or how to revise the plans, and then making those suggestions in such a way that the human can make sense of the suggestions. So that means they are expected, in the context of the task model that the human has, rather than just the task model that the robot has. So that's sort of one set of applications. There are, in fact, there's, I think, this most recent IIII, we have a demo on using this kind of technology to provide mission planning support, decision support systems. Okay. And then I also mentioned to you a while back, this Tathagata and Karthik and I think Jeff Kephart actually worked on this Mr. Jones, which essentially uses some of the same ideas that were developed in our group in terms of providing explanations for the decisions when the intelligent room is essentially trying to anticipate and provide additional decision support to the humans in the loop. So in the case of Mr. Jones, essentially, they basically provided, using these kinds of technology, they were able to help the transparency of the decision-making process. The smart room essentially makes its decision-making process more interpretable to the human in the loop. And they use this idea called externalizing the brain, which is sort of can be made sense of in terms of these models that I have talked to you about. One other thing is, if in fact, in the case of that robot scenario that I mentioned, both human and the robot started with the same model of the environment. So MRH can be initialized to MR in the beginning, but then then you only need to track the drift. The AI agent only needs to track the drift. It turns out that some cases you may not have that ability, and so you may have to learn this MRH model. And we have done a bunch of work in how the AI agent can learn the human's model, and also to avoid, to handle vocabulary differences. For example, as I said, in some cases they start with the same model, so you don't need to do anything special. Even if the robot doesn't know the model MRH with certainty, it can reason with multiple potential models that the human might have and provide explanations that sort of would make sense irrespective of the set of models that the human has. This is a kind of notion called conformant explanations that will make sense in the context of any of the models that the human might be having. So you can do that. You can develop, you can extend the idea of explanations into these conformant explanations. In other cases, the AI agent does also have to actually learn the human mental models from past traces. The only interesting thing is there's a lot of work actually in learning planning models from behavior traces, both in multiple communities, both in planning community and reinforcement learning community. One important distinction is that we are trying to learn MRH, not MHR. So the way humans might do the problem might well be different from what the humans expect the robot to be doing the problem. And what we need to learn is MRH, and getting the traces for that is somewhat trickier. And we talk about it, in terms of how to ensure that. So in essence, you have to actually provide a critiquing opportunity for the humans about robot behaviors, and from that learn the implicit model that they have for MRH. Okay, and then of course we also can talk about what happens if the vocabulary differences exist. That means the humans and machines actually are using very different kinds of models, either PDL models with different vocabulary, or one uses PDL model, let's say, and the other uses an inscrutable model. And we have done some work on that. I'll quickly give you a sense of that. In the context of learning the model, the MRH from traces, essentially what we do, this is some work, in ICRA 2017, what we do is we learn this as a labeling function from the humans critiquing previous robot behaviors, and then that labeling function then becomes a stand-in for MRH. Remember that MRH doesn't have to be an executable model. It only needs to be a model that allows the agent to see how far the behavior it is putting together is going to be far from the human's expectation. So these labeling models can be learned from the traces. It turns out that it also can be extended. The same idea can be extended even when there are explanatory messages involved. There, the training data will involve robot behavior along with explanatory messages, and seeing how the humans label that behavior in terms of it being interpretable or not, and using those labels to get an approximation of MRH. And there's a paper in 2019, Ishkai, which does that. So in a weird way, you can think of this as a model-free model reconciliation, because the other model, MRH, is actually being implicitly represented. And you are still able to provide explanations in trying to get the models closer together. So now, one last thing, hopefully I'll get through before maybe opening up for questions, is What if the vocabulary is different? Till now, we have sort of focused on scenarios where the models may differ in terms of preconditions, effects, abstraction levels, etc. But they tend to still have the same vocabulary. But when AI agent uses representations that are inscrutable to the human in the loop, so the AI agent is using a very different reasoning methodology, maybe some deep reinforcement learning technique or something, and the humans have a symbolic understanding of the problem. And then how do you do explanations? The popular machine learning answer, in fact, when you hear about XAI, is this sort of thing. Popular machine learning answer to date has been to focus on exchanging the explanations at the lowest common denominator substrate that the machine shares with the human, which is essentially images and videos, images and space-time tubes. Okay. So, for example, to provide an explanation as to why the machine thinks this particular picture is a picture of husky, Alaskan husky, it might show the regions in the image that were most responsible for its decision, and that those regions might mean something to the humans in the loop. In this particular case, this is a one-shot decision, so you're just showing an image. If it is a sequential decision, the machine essentially has to show a video with annotations on the video, and then hope that the humans will understand the reasons. Okay, so this is actually pretty bad. I would argue that human civilization has been to the whole point of human civilization has been to get away from exchanging space-time tubes. We developed symbolic means of collaboration just so that we don't have to exchange space-time tubes whenever we need to explain to each other. So XAI is hard, but mostly as a debugging tool for inscrutable representations. And we basically just sort of point to pieces of the image or the video tube. Video tube stuff hasn't really been done that much, but mostly images has been done. And that pointing really decisions involves for the sequential problems that will involve pointing over space-time tubes. Explanations are critical for collaboration, but they're really not supposed to be about pointing to the space-time tubes, because that's just way too costly a way of interacting and providing explanations. In particular, actually, let me skip this and then say that, in particular, pointing explanations are very hard to comprehend. Here is a very simple thing that I want to ask you. After I give this talk, you will have the video of this talk that Rama is going to keep. Are you going to be looking at the video, or are you going to ask for my talk slides? And if you ask for my talk slides, you have to ask yourself, why do I want talk slides when I have the video already? Because space-time tubes are very painful to actually comprehend. They take longer time. There's higher cognitive load on people. So we always want simple symbolic explanations. And so humans essentially developed shared symbolic vocabulary and use that to exchange symbolic explanations where possible, and then come down to pointing explanations only when everything else fails and vocabulary is truly inadequate. And this is typically seen as the reason to expand your vocabulary. And this approach works particularly well for explicit knowledge tasks, but we also use it for mixed and tacit knowledge tasks. For those of you who are basketball fans, basketball is very little explicit knowledge, and yet things like pick and roll, which is like a space-time tube, or a class of space-time tubes, are essentially, you give it a symbolic name and use that to make sense of what a player is doing, and also give explanations to others in terms of your understanding of the game, in terms of this symbolic vocabulary. So, to cut a long story short, we are currently extending our model reconciliation framework to support such learned symbolic explanations. And this work is quite new now. So there was a paper in ICML workshop last year, and it's also under review right now, where essentially the machine can do its reasoning in any inscrutable way it needs, but when it needs to provide an explanation to the human, the saliency region or the annotated region that it has, it needs to convert it into a symbolic approximation and then provide it to the human. So the machine really, even if it doesn't think in terms of these precondition effect representations, it needs to approximate what humans are thinking in those terms just so that it can provide symbolic explanations. This is actually a very interesting extension which keeps all the theory about explanation generation, etc., still valid. But now you are talking also about this sort of concept acquisition as well as approximating the explanations in terms of the concepts that you have. It turns out these sorts of things can also be used for single decision tasks, such as classification. There's some work that we have shown that instead of just trying to decide how good a classification system is in terms of purely on its accuracy, you should be also looking at the kinds of errors it does and how inexplicable its errors are. In fact, you're more likely to lose the trust in a classification system, not just because it made a wrong diagnosis, but it was like way off. So for example, in these pictures, you'll notice that there is a tabby, and some of the state-of-the-art systems will say the tabby, the cat, they'll say that's a remote control. And by making sure that you take the explicable misclassification into account, the kinds of errors that come not just from accuracy, but also from how inaccurate you are when you are misclassifying. Our system says in this case that it's tiger cat. So these are only the places where in fact there is inaccurate decisions are being made. But when we make inaccurate decisions, they're a lot more closer to be in the ballpark than the existing system. So this is sort of, again, taking into account not just what is right, but also how far are you from the human's expectations. There's a bunch of things that we can still talk about. One last thing that probably I want to talk about is foil-based dialogue, because that actually corresponds to one of the applications at IBM that I mentioned earlier. So in addition to just the way we were providing explanations before, is that the machine just sort of realizes how much the human's model has to change, and it computes that delta and provides that to the human. It turns out that then the expectation is that with that change in the model, the humans are able to compute the optimal plan in the new changed model and realize that it's the same as what the robot is doing, and they're happy. Sometimes actually this requires inferential capabilities that the humans may not have. And so, for a robot, it might well be an AI agent, it might be fine enough, but a human might not be able to quickly compute the new optimal plan. And so a better way of interaction, an alternative way of interaction, is to let the human ask, why did you do this plan as against this other plan? So this other plan that the human provides is a foil, and the robot then needs to only provide an explanation as to why the foil is not as good as the plan it made. And in explaining it, it ensures that only the model changes, the changes to be made to the model that the human has are going to be just enough to show that this foil is worse than what the robot has already done. Okay. It turns out that this is an alternative way of interaction, foil-based interaction. There's a whole bunch of a sequence of papers on this that, in fact, one of my students, Sharad Sridharan, has done. And these sort of explanations can be done in terms of, both at the, at different levels of abstraction, allowing, for example, for the humans, the possibility that the humans have a more abstract understanding of the model than that the robot has. It turns out that is actually, and when there is a foil being presented by the human, you not only want to provide an explanation as to why the foil is not possible, you should also realize that that is a silent cry for help by the human, saying, I would have been happier if you did this kind of a plan as against the plan that you made. And so you would then take that as an opportunity. You, the AI agent, will take that as an opportunity to replan, to revise your plan to be as close to the human's one as possible in the next iteration. And so that sort of is a fuller foil-based dialogue, where you not only are providing explanation as to why the exact foil cannot be done, but you can then use that as an implicit indication of the preferences the human has, and come up with the next suggestion that is closer are closer to those preferences. We have actually used this in the context of these decision support systems like radar, and the previous poster is from IEEE 21 demonstration. we can use the same sort of technology to also provide an explanation of unsolvability of a problem when the machine cannot solve the problem and the human doesn't understand why the machine is not able to solve the problem. It can provide an explanation that the human can understand at the right level of abstraction. There is a nice paper in Ichikai that talks about the level of the automatically computing the level of abstraction and showing the set of sub goals that would needed to that the agent had to go through in that abstract model and why that cannot be done. And that will become an explanation for the human. The reason I dragged you through all this is actually the technology that pretty much was used in this model acquisitions for dialogue planning, which is this IBM research project last year with Tadhagata, Christian Musi, and Sharat Sridharan. So this was a system that basically was being used in the context of dialogue planning, and the dialogue plans models are being written by the humans, but they can make the models be wrong. And this technology of unsolvability explanations becomes a way in which you provide symbolic help to the humans to debug their own models. Okay, so that the humans can actually make the right kind of changes, and then the dialogue, and then the new dialogue plan can still be used. So that is something.
I just wanted to point out, Rao, that we have 1.5 minutes left. Yeah.
Okay. So I will basically. So that's basically the that particular project. I am going to skip over all of this, and actually, I think I will just sort of. Let me see if I can. We do human subject studies. I don't want to go into that. There's a bunch of ethical quandaries that, as I said, head fakes and so on, that become very important. In fact, we show that we can use the same sorts of technologies to do deception. Not only can you be interpretable to the machine, but you can also deceive the machine. And the same sort of technology is just the other side of the flip side of the coin. This is Anaka. In one case, the robot wants her to see what it is doing. In the other case, the robot doesn't want her to see. So it essentially ensures the partial observability, the right kind of observability, by distracting Anaka in this particular case. So deception is also possible. There's a nice paper that Tadhagata wrote a couple of years back about how the model reconciliation techniques can be used for telling lies of omission as well as lies of commission. I'm not saying that you want AI systems to be telling you lies, but you want to understand how this technology can be used as well as misused. And that's kind of important. So there's a paper in AIES on that. And I'll end here. Basically, in summary, I want you to kind of remember that effective human AI interaction requires systems to be able to manage human mental models, and managing models brings up both inference and learning challenges. And we have done a bunch of work in sort of developing these technologies and doing applications in the context of embodied human-robot teaming, decision support, as well as in this last thing, this model acquisition case for IBM. There's a monograph on explainable human AI interaction that's coming out in summer. And then there's also this AI magazine article on challenges of human AI. I will stop there at that point. Thank you.
Thank you so much, Rao. Really appreciate it. I find it fascinating to find this balance between, conforming to what humans think versus what AI agents explain. Should they explain everything versus explaining important decisions? And you brought those points out very effectively in your talk, and that has applicability across the board in all of the AI applications that we are building, be it in incident management or in business process management, and whichever area where we are building products within IBM. So I find it very relevant, and also the importance of user feedback to the system and how the AI agent can refine its models based on the feedback. And the last one about foil-based explanations is also an interesting one to do this explanation. Instead of trying to explain everything, why not let the user ask specifically, hey, why didn't you do that? Why didn't you do this? And let the system explain. So these are all very interesting concepts that we took away from your talk. Really appreciate you taking the time to come in and share your research work with us all. Given the time we are over, unfortunately, we may not have time for any questions, but if anybody has time, feel free to stay on for maybe for a minute or two to ask any last minute question you want to get answered. If not, we will follow up. Feel free to follow up with Dr. Rao, or follow him on Twitter and other social media channels where he often
And,
shares.
and also, as I mentioned, Tathagata is at IBM Research in Cambridge, as well as Karthik. I don't know exactly where they are physically. Nobody knows anybody where anybody is physically, but they are both with IBM Research, and they're actually connected to some of the lines of work that I have talked about. So you have some in-house expertise on this too.
Absolutely. So if I know we are over, but if anybody want to have one question, unmute yourself and ask. If not, we can
I
close.
have millions of questions actually. Well, thank you for amazing talk. I guess a couple of questions mixed into one. What happens if the problem is just the execution and the models are the same? Right?
So the execution is the problem essentially. So the interesting thing is that the model the robot has of the task is itself an abstraction of the real world. And so if there is an execution problem, then there is an M star, which is the environment's true model to stand in for the true model. And the replanning there essentially is with respect to MR versus M star. That's what normally planning, when we talk about replanning, essentially this thing didn't work. And so my current model of the environment is wrong. Typically, environment doesn't provide nice and clean explanations to you, while intelligent agents do provide nice and clean explanations to each other. So in the case of environment, essentially, either you replan or you learn from these failures and improve your model, MR, slowly at, over a period of time. That's pretty much what is happening in reinforcement learning in essence, because you have a partial model of the environment, and then things are not going according to the plan. And then over a period of time, slowly you are changing the model, right? So that's what I would say. The reconciliation is occurring there too, except there is no explanation. Environment doesn't sit down and say, you have this problem with your model. You just have to, in essence,
But I would claim that's more or less the same, right? Because when the robots plan when they start with the same model and then the robot actually executes something and then it sees that it cannot continue the execution of that plan, it needs to replan now, there is a failure somewhere, right? And it's either a failure to execute the next action or execution of the current action results in a state where the robot realized that the rest of the plan will not lead it to the goal, right? And right, so then that moment is the change in your view of the model, and the robot will change its model and propagate it to the human, right?
I think the larger point, Mikhail, is that essentially environment never conforms to anybody's model. It is what it is. And the agent tries to learn the environment model. So in our case, actually, the parallel would be the human might think that the robot should be doing something and the robot didn't do it, let's say. They might learn over a period of time that their model is wrong and they will improve it themselves. This is one of the funny things about explicability. If the robot is doing something unexpected first time, the humans are surprised. If it is doing it a second time, they're less surprised. By 19th time, they are no longer surprised. And so what was originally inexplicable has become explicable because the humans changed their model from the observation that they had of the robot. And their learning typically is much more sample efficient. And that is a different issue from what I'm talking about, which is the robot trying to actually make humans' life simpler by proactively either conforming to the explanations or providing a heads up when it cannot conform, by telling them what pieces to change, which is the kind of thing that the environment never did it for us. But we do it to each other. That's the big point. That's a big difference to understand. There's connection to replanning, but the bigger difference is here, in the case of classical replanning, if the environment started talking to you, if you believed in the god of environments, who is a good friend of yours, they would then be using model reconciliation to tell you. Of course, if they're gods, they can actually change your brain directly, but that's basically the parallel with respect to the talk that we're doing here.
Right.
Thank
So-
you. How about, may I suggest please take it up with Rao offline. We are 7 minutes over actually. So I'm afraid we'll have to leave it at that. But once again, thank you so much, Rao, for coming on board on a reasonably short notice and sharing such valuable insights and work with us. Appreciate it.
Thank you.
I'll stop the recording now.
Okay.